Right, as we've indicated, we are looking at this eigenvalue problem, and the matrix A has been given, and we have its inverse as well, has already been given, so we don't have to compute that. Although obviously we know how to compute inverses of matrices using methods in linear algebra. Okay, right, we have broken down the question first. Things first, we need to be able to find the dominant eigenvalue and associated eigenvector. The question is which eigenvalue is dominant and which one is the associated one? Okay, right. So to answer that question, we shall look at the idea of what to call the Jacobian circles. Right. So the idea of what to call the Jacobian circles. Right. We have the Jacobian um Jacobian circle. Okay, there are these special types of circles this that need to learn. So these Jacobian circle theorems. Okay, there are two of them we shall learn. Right. Circle theorems, two of them. Right. Are formulated as follows. Right. So these circle theorems are formulated as follows. But first, we shall look at theorem one. Right. We shall look at theorem one. What does this theorem say? So in this case, we let A be an n by n matrix. Okay. Normally in the exam they give smaller matrices, but yeah, 2 by 2 are very popular. But you can always obviously find a 3 by 3 like this one. With the AIJs real or complex. So in other words, we're looking at this being an n by n matrix with the AIJs real or complex valued. So we're taking the AIJs are just the entries in the matrix which are either real or complex valued. Then we say, then all the eigenvalues of A, okay, this is a very important theorem in terms of the classifications of these eigenvalues of the matrix A. Right. So then all the eigenvalues of A lie in the union. Okay, I'm stating this because the theorem is it's a law. It's very important that it is understood. Right. Right. In the union of the following n disks. Right. It's very important that it is understood. No one is going to ask you to state it, but it's very important for us to just be sure of what it states as we're going to use it in this question. In the complex plane. Right. And what we then say, we state the di. D subscript I is defined as the set that contains all the complex numbers z in C and z minus AII less than or equal to the summation j equals I, j not equal to I, AIJ The i's are 1, 2, up to n. Okay, so we shall look at what this definition says. So we are defining a couple of disks from the matrices. And the disks are, we take a complex number z, we then subtract the AII, which are the entries. A11 is -6, A22 is 9, A33 is 5. So these entries are the entries in the main diagonal, and these are the entries that are off the diagonal. Right, so we're going to look at what that means, obviously with a couple of examples here, but before now next to that, we shall do the following. So we shall say, right, we note the fact that DI is simply the disk with center, AII, and radius. And radius equal to, setting the law we use, equal to the sum of the absolute values. Right. Of the absolute values of the entries. Okay. In row I, which are not on the main diagonal. Okay. So this is the first theorem. So this one here is theorem 1, the first theorem of the Gershgorin circle theorems. And we give the statement as follows. We say let A be an n by n matrix. Like in this case, it is actually A is a 3 by 3 matrix, or it's a square matrix whose number of rows equals the number of columns. And with the Aij is real or complex, so the entries can be either real or complex, right? Then all the eigenvalues of A lie in the union of the following n disks, right? The Di. So all the eigenvalues of A will lie in the union of the disks. So these disks here, if you take the union, because the disk is a set, right? So that is a set that is full, right, shaded inside. So a disk would be, for instance, if you have z minus 2, give you an example, is less than 1, it would be a disk that is of radius 1 and center 2. Right. So obviously you can plot that one. Okay, we're gonna look at things like that. So if at this point we have 2 is x, right? Because if it's 2, then it is z minus. Okay, we'll look at examples. These things are real here. So that's gonna be right. It's gonna be 2 plus 0i plus 0i. So we are dealing with the center, this one, in radius 1. So it's gonna be a disk like this, radius 1. Okay, it's going to be up to 1 here. And then you shade inside because it is less than or equal to. Okay, it contains the boundary. So you have those kinds of disks. Right. So just take note of that. Okay, we're going to look at those in detail. But these are like circles. I know my drawing is not a perfect circle. But now this theorem 2. So the first one says that all the eigenvalues will lie in the union of the disks. So now if you have another disk and now you actually take the another disk here, maybe another disk is here, another disk is there. So you take a union of them. So you have the eigenvalues lying inside these disks. These disks are basically circles, but we proceed to state the next one. Right, we proceed to state the next rule here. And now we then say theorem 2. Right. So theorem 2 of the Jacobian circles is extremely important. You say if they lie in the union of the disks, what next we say? We say that if k of this, okay, is a number, right, of these disks, okay, do not touch. This is very important because do they touch each other, and what are the positions of these in the two-dimensional space, right? If k of these disks do not touch, um, the other nk disks, then exactly k eigenvalues. Counting multiplicities. Counting multiplicities. Lie in the union of those k disks. Okay, we'll look at what this means. Right, of those k disks. Right, so at this point, we are effectively then saying, right, so you have in theorem 2 here, that if k of these disks do not touch the n minus k disks, then exactly k eigenvalues, counting multiplicities, lie in the union of those k disks. Right, so let's look at the example so that we can understand this better. For the matrix A, we have what this means. It's better explained with examples. Better explained with examples. Right. So for the matrix A, for the matrix A above, we have, right, so we're going to have D1, disk 1. Okay, we continue. Right. Okay, continue. Right, so we have disk 1, for example, for the matrix A. What would disk 1 be? So disk 1 will contain all the complex numbers Z, right, such that you have Z minus. Okay, let's look at the matrix A. The matrix A has minus A11 is minus 6. So we're going to take the minus 6 here because it's A11, then there is A22, then there is A33, which is 5. A22 is 9. A11 is minus 6. So we're going to take first the A11, and then you subtract that one, like this. And then it's less than or equal to, right, so we have, you add those that are off the diagonal, right? If you take the A11 off the diagonal are 0, 6. You add them up. You take the modulus of those, the modulus of each. So it's going to be the modulus of this one here, the modulus of the 0, and the modulus of the 6. And if you add them up, you get 6. All right, so you have D2, which contains Z in the complex numbers, Z minus. So the next one, A22, is 9. but of the diagonal are 4 and 2. You're going to say z minus 9. But of the diagonal, we saw that 4 and 2. So we add the modulus of each, and the result is 6. Disk number 3, because it's 3 by 3, so it has 3 disks. Right, so 3 Gaussian disks. Right, so we have this one and Z minus. So we look at the other one, A33 is 5, but of the diagonal entry along the third row is actually 3 and 0. But you take the modulus, so it's the modulus of minus 3, making it 3. So that's minus 5 here. And then you take the modulus of minus 3, and also you take the modulus of 0. And the result is 3. So we continue. Right, so according to the Gaussian circles, right, according to the Gaussian 1 and 2, right, so we have that one eigenvalue lies in D1. Why one eigenvalue lies in D1, and the other two lie in the union of D2 and 3. Okay, we're going to analyze that together. According to the Gaussian 1 and 2, why one eigenvalue lies in disk 1 and the other one lies in disk 2. Right, so we have seen that if k of these disks, according to theorem 2, if k of these disks do not touch the other n minus k disks, then exactly k eigenvalues, counting multiplicities, lie in the union of those disks. So we have seen that for the matrix A, we have disk 1, disk 2, disk 3. Right, we're going to look at the geometry of these disks. Right, looking at the geometry of these disks, we can really see that there is one disk that has center, right. So this one is going to have a given center. Okay, I want us to look at the centers here. The center is 9, the center is 5, but here is negative, negative, so the center is going to be, so it's going to be z plus 6, so the center is minus 6. Right, so if you look at these, which disks touch, which disks do not touch. Right, so we are looking at these disks and we're looking at the geometry of those disks. Because if k of these disks do not touch the others, so you take some disks, if some disks do not touch the others, then exactly k eigenvalues of those that do not touch will lie in the union of those k disks. Okay, you're going to understand what that means precisely as we give this description here. So we shall verify these by calculating the eigenvalues in the vectors analytically. We shall verify these by just verify these theorems by calculating the eigenvalues and seeing exactly what this means, calculating the vectors analytically. Okay, so how do we find the eigenvalues? Right, to find the eigenvalues so that we can interpret these analytically. Let's look at the eigenvalues we have. Right, so we are going to calculate the eigenvalues. How do we find the eigenvalues? verify this theorem. Right, to find the eigenvalues, we start with AX. We say AX equals lambda X. That is how we start. And therefore, this means that A minus lambda, we multiply by the identity matrix, and we multiply by the vector X. Right, so the eigenvalues found at, let me start from the margin. Right, so the eigenvalue that it's obtained as follows. The eigenvalues are obtained as follows. What is the matrix here? Minus 6, then you subtract lambda. We have 4 minus 3. Okay, this is the matrix A, but you're just subtracting lambda along the main diagonal. So the matrix A has these entries, but you're just going to say minus lambda, minus lambda, minus lambda, and the rest of the entries are the same. So that's what we're going to do. So we're going to say 0 here, then 6, then there's a 9 here. We subtract lambda from it. There's 0, and then we have 5, subtract lambda. Okay, we are finding the eigenvalues to verify the validity of these theorems. Right, so if you find the determinant of this, we just need to find the determinant of this. How do we find the determinant of these? Okay, we can expand along the second column. Right, expanding along this column here, we shall have positive, negative, negative, positive. So it's just going to be positive 9 minus lambda. So we block this and that. Okay, so you're going to have just one entry, but you block this and that, which is going to be minus 6 minus lambda. That's the determinant from first year. And then we have minus 3, minus 3, 5 minus lambda. Okay, and then we just compute the determinant. How do you find the determinant? You just cross the entries. So that's going to be 9 minus lambda into minus 6 minus lambda, 5 minus lambda, plus 18 is equal to 0. So we have, this one is minus 30. This is exactly 6 lambda minus 5 lambda plus lambda squared plus 18 equals 0. Okay, we might not even say equal to 0 yet. So you can just go on that way. Right, so we have this. We continue. So this is the same as 9 minus lambda into lambda squared, just grouping like terms, plus lambda minus 12. Okay. 9 minus lambda into lambda plus 4, and then lambda minus 3. Okay, I want to just verify which eigenvalues lie in which disk. That's what we want to verify here. So we're finding the eigenvalues. Right, the quadratic equation is when we equate this to 0.
Hello?
Yes, please.
How did you get 18?
How did I get 18? So we multiplied minus 3 and 6, but it's negative. So we've cross multiplied this with that, and multiplied. We said minus 3 and minus this times that. But if we say minus this times that, it's already negative. So it's going to make it plus. Okay. In the same way that if you say the determinant of A, B, C, D, what is the determinant of this? Right, so determinant of these, you cross multiply these, so it becomes AD minus BB, for example. Okay, so by using this formula. Right, so if I use this formula, then we're able to get exactly the determinant. So it's minus this times that, which gives plus 18. Okay, right, so we continue then, but we're going to look at the characteristic equation. Hence the characteristic equation. Hence the characteristic equation is, what is the characteristic equation? So we equate that to 0. So it's 9 minus lambda from the previous page. But we have lambda plus 4. And we have lambda minus 3, 0. So here we have that lambda is 9 minus 4, lambda is 3. All right, so what is this? What does this mean? So I'm going to write a description of what is happening here in view of the theorems. So basically, this confirms the theorems. This confirms our earlier conclusion in view of the Geschorian circles, because minus 4 lies in disk 1. Okay, shall get to that together. While 3 and 9 lie in disk 2 union disk 3. Let's look at this. Where is lambda equals 9? Where does lambda equals 9 lie? And where does the other one lie? Okay, so we look at that quickly. Right, so first things first, we realize that we have these Geschorian circles, and we have that this disk here is z plus 6 is less than 6, less or equal to 6, and therefore it's a disk is centered at minus 6 of radius 6. For now, if it's centered at 6 and the distance is 6, its radius it's rather 6. It can go, okay, I'm gonna look at the sketch of this. Right, so it can go as much as 12 units away from 6 on the x-axis. So it goes 12 units and then it touches the origin. 12 units. So if it's 12 units, this one is like lambda equals 9. So lambda equals 9 units will surely be included there. Okay, I'm going to look at the geometry of this. I'm going to sketch this and look at what this means. Right, so now if you look at minus 4, right, so where does minus 4 lie? We actually say, therefore, minus 4 will lie in disk 1. Right, so lambda equals to minus 4 will lie disk 1. So where is lambda equals to minus 4? Right, so lambda equals minus 4 is a real number that is which is real, and therefore it is at x equal to minus 4. Right, and we argue that it lies in disk 1. And then we have the others. Okay, let's just look at this geometry. Right, so let's look at the geometry of this. Okay, right, so this one is like the imaginary axis, and this is the real axis. Let's look at disk 1. Okay, disk 1 is z plus 6 is less or equal to 6. So we have you make these 0, so it's z equal to minus 6. So you have z equal to minus 6. Right, so if z is equal to minus 6, what do we have? If z equal to minus 6, then you count 6 units. It's a circle you need to draw. I'm doing the wrong thing here. Making a mistake here. Right, so this is minus, so it must be on the other side. Like minus that. So yeah, can I do something nicer? Right, you can do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right, so this is like -1, -2, -3, -4, -5, something like that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you have -6. -6 for because it doesn't have it doesn't have I this. So it's sitting at -6, and then you found you want to draw this disk, so it's gonna be at 6 units away from this. So if it's 5 here, and then how do you count 6 units? So it's gonna be here. It's gonna be counting 1, 2, 3, 4, 5, 6 units. Okay, so it's gonna be here. And then now it's gonna count. So you're gonna be having a point here, and then you're gonna count again 1, 2, 3, 4, 5, 6. You're gonna have another one here. So if this one is -6, right? -7, -8, -9, -10, -11, -12. And then you do this like that. Okay, this is not to scale, but trying to make the concept clearer. So you have this disk, this is disk 1. Z plus 6 is Z equal to 6. Okay, so this must be a perfect circle, but yeah. Right, let's look at the next one. What is disk 2? So we're looking at the fact that -4 lies in disk 1. Yes, here is the number, -4. So there's lambda equals to -4. Surely it lies in disk 1. And that is true. And then now we just need to look at the others. Okay. And then now, what about disk 2? Disk 2 is in center 9, z equals 9, and then radius 6. Right. So let's look at 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. And then at 9, you count 6 units. Radius 6. So radius 6 is 1. It's 1, 2, 3, 4, 5, 6. Okay, so this is 8, 7, 6, 5, 4, 3. So then it's going to count. Okay, I was supposed to extend the original axis, the horizontal axis here. So this must just go on like this. So if it's 6 units, so it's going to be like 15 here. Okay, so it means therefore lambda equals 3. There's an eigenvalue that is 3, so 3 is here. Lambda equals 3, but there's also lambda equals 9. Right, so lambda equals -4. Okay, what is the other disk? Okay, this one is D2, this one. Excuse me. Okay, I'm going to remove this one. Okay, because this is D2, which is Z plus -9 is less equal to 6. Okay, can I remove this one here? Okay. So now there's another disk that is the third one. Center 5, z equals 5. So we're going to look at 5 on the real axis, and then the radius is 3 units. Then I'm going to make it red, because now everything is blue. I'm going to have so much confusion here. So we're going to make it red, center 5, and radius 3 units. So it's going to be 1, 2, 3. And then it's going to be 1, 2, 3. Okay, so you have this. Okay, so you have this. Right, so we can see therefore that in this is disk 3. Okay, let's see now. This one is lambda equals 9, and then there's lambda equals 3 is actually in the other two. Obviously, you can see that these two disks do not touch. The 3 disks, okay. One disk is separate, only 2 disks touch. And hence theorem 2 that says that if k of these disks do not touch the other n minus k disks, right? If k of these disks do not touch the other disks, so here we have that one disk doesn't touch the other 2 disks. So you have k disks versus n minus k disks. Okay, in our context, it's one disk versus does not touch 3 disks minus 1 does not touch 2 disks. Then what? If 1 does not touch 2 disks, then what? If k of these disks do not touch the other disks, then exactly k eigenvalues, counting multiplicities, lie in the union of those disks. Right, of those disks. Right, so one way to look at that is to say, if you are to look at these as k disks in view of the theorem, and this one is n minus k disks, and therefore if you have 2 disks do not touch 3, do not touch 3 minus what? 3 minus 1, which is 3 minus 2. Okay, because this is 2, so it's 3, which is minus 3 minus 2, which is 1. Do not touch the 3 minus 2, which is 1 disk. All right, so we have that. I'm getting back quickly. Okay, so if the 2 disks do not touch the others, okay, I want to remove the S. Yeah, right. If 2 disks do not touch the 1 disk, then according to that theorem, which is what it implies here, right, then exactly k eigenvalues. In this case, it would be then 2 eigenvalues because we're looking at those 2 disks that do not touch the 1 disk. So then 2 eigenvalues counting multiplicities lie in the union of those disks. So we can see therefore, because the union is big, so it contains more eigenvalues. So in other words, you'd have that 2 eigenvalues will lie in the union, of those disks that do not touch the other disk. Okay, so it is true in this case, right? That the two eigenvalues, so we verified two eigenvalues lie in D2 union D3, and one eigenvalue lies in D1. One eigenvalue lies in D1. Lies in D1. Okay, good. Okay, we're just looking at these. Okay, obviously this is very important because it is important to us when you look at the power method and these kinds of notions. These are very, very examinable, so we need to discuss them. Okay. Now also let's see now. There is another statement here I want us to verify. Theorem 1. If we let A be an n by n matrix, in this case 3 by 3, with the Aij is real or complex valued, then all the eigenvalues of A lie in the union of the following disks in the complex plane. We have seen that the eigenvalues of A will lie in the... So obviously theorem 1 is just about the fact that the eigenvalues will always be found in the disks. But the second theorem is to do with touching and non-touching disks. Okay, and which eigenvalues lie where. Okay. Okay, I want to mention something very important here. Right. Right. Okay, I want to include something else. We need to include the idea of what we call the eigenvectors. We need to include the eigenvectors, okay, because this question is about, this question says the dominant eigenvalue and the associated eigenvector. So we're going to actually look at the idea of the dominant eigenvalue here. Right, so the dominant eigenvalue and the associated eigenvector. Okay, so we need to still continue and solve this question here. Right, we still need to continue and solve this question here. Right, so we still have some good amount of calculations to do. Right, so we are effectively then saying here, we need to do the eigenvector for us to be in a position to find the dominant eigenvalue and the associated eigenvector. Right, the associated eigenvector. So we need to find the eigenvectors. Right, let's look at the eigenvectors. So the eigenvectors now. Eigenvectors. Right, so the eigenvectors would be lambda. We have -4 first. Right. And then the other two. Where do we find the eigenvectors? We find them from the equation A minus lambda I equals 0. Okay, so we come here, A minus lambda I, x equals 0. Okay, so we would remember that it is -6 minus lambda, that matrix we wrote with the eigenvalues. Subtract lambda here, and it was 0, 6. And then we had 9 minus lambda, and then we had 0. We had 5 minus lambda, and then we had x1, x2. Okay, this method of the eigenvectors is found in linear algebra, so there's nothing very peculiar in this module. Right, so obviously we continue. We substitute straight into this, so is minus into -4. Goodness me, 4 minus 3, 0. 9 minus into -4, 0. Okay, there's a 0 here. There's a 2. There's a 2 in that original matrix A. Right, so you have 6, 2, 5 minus into -4, which is x1, x2, x3. 0, 0, 0. So, what is all this thing here? Okay, let's just add this. This is going to be -6 plus 4, -2. 13, -3, 0. x1, x2, x3. Okay, I want to get the eigenvectors, associated eigenvector. Right. So we have that. We have exactly that. What is the eigenvector? So to find the eigenvector, you need to do row reduction of this. So we proceed to look at the augmented matrix. -206, we have 4, 13, 2. We have -309. Augmented matrix, you put 0, 0, 0. Can always leave out, some books will leave out the zeros. Just form a matrix without the zeros. -1, 2, row 1. 1, 0, -3, 0. Okay. This one, plus 2, row 1. 0, 13, 2 of that, 12 plus 2, 14, 0. Okay, 3090. Okay, let me continue. So row 3 plus 3, row 1. Yes, -3, 0. Plus 3, row 1 is going to be exactly, okay, let's leave row 2 like that. 14, 0. 3, row 1 is going to be 0 here. 0, 0, 0. Okay. So we get this. Okay, this looks like I've written this too far, way too far, but it's not really way too far. Right, it's not really way too far. What is this? Right, so I'm just bringing this closer. Right, I'm bringing this closer. What am I bringing closer? I'm removing just this bracket and bring it closer. It's far, it's further away. It's further away, so obviously we're gonna close this one. Right, so you're gonna close like this. And then here we said row 3. That was a row operation, elementary row operation, plus 3, row 1. Okay, now further reduction is not possible at this point. So you can leave here. You can then get the vector here. So this is going to be x1 minus 3. x3 is 0. 13 x2 plus 14 x3 is 0. x3 is x3. x1 is 3x3. x2 is minus 14 over 13 x3, and x3 is x3. Eigenvector. The eigenvector is x1, x2, x3. You can write it as a row. You can write it as a column. Okay, it was written as a, it's popular to write it like this in this module. That's just a row like this, just the point. Okay, it's convenient. So what is x1? Is actually 3, x3. Right. You can let, right, so you can let x3 be m. You can let it be anything. It becomes convenient that way. So if you let it be m, right, what do you get? Let x3 be m, Excuse me. So if it is m, then we have x1 is going to be 3m. x2 is minus 14 over 13m. x3 is m. So you get this one. Pull out the m. So this is exactly 3 minus 14 out of 13, 1. The m is arbitrary. Okay, so we get one eigenvector for the lambda equals what? For lambda equals minus 4. And then you continue to find the other eigenvector for each one of those. 3 and 9. We have a bit more work, these eigenvectors. Right, so for this one now. Okay, one of the eigenvectors was 3. Eigenvalues, excuse me. Lambda was 3. So we have the formula for finding the eigenvectors is this one. X which is minus that minus, you can say minus 3. 4 minus 3. Okay, matrix A was 0, 6, then it was 9 minus 3, 2, 0, then we have 5 minus 3. So just subtracting 3. And then we have x1, x2, x3, which is 0, 0, 0. 0, 6, 4, 6, 2, 2, 3. And this means we can write the augmented matrix. Minus 9, 0, 6, 0. Goodness me. 4, 6, 2, 0. Okay, minus 3, 0, 2, 0. Okay, we do what we did before. We just reduce this one to reduce the echelon form, like in linear algebra. We want to get the eigenvectors associated with lambda equals this one. Okay, just practicing with this. Okay, because we will have to classify the smaller eigenvalues, the smaller eigenvectors, and things like those. So, right, we are practicing with this. Okay, we just let's see now here what we get here. Right. So we can multiply by minus 1/9, row 1. 1, 0 minus 2/3. 462, 0. Minus 302. So row 2 minus 4, row 1. Row 3 plus 3, row 1. 1, 0 minus 2 over 3, 0. Minus 4 that, 0. Minus 4 that, 6. Minus 4 that is 8 over 3. 8 over 3 plus 2. What is this? 14 over 3. Right, so we come to the third row. Row 3 plus 3, row 1, 0. Plus 3 that, 0. Row 3 plus 3 that, which is minus 2, 0. 0. Okay. Now the question becomes, any reduction possible here? Is any reduction really possible here? Is any reduction possible here at this point? Well, it is not possible, quite. So we have the reduced original form, and therefore we can continue. And say x1 is 2 with x1 is 2 with 3, x3, x6, x2 is 14 out of 3 minus 40 out of 3, x3. So, which means x2 is minus 14 out of 18. Divide by 6 both sides, and you get this. Okay. Important further simplification is x2. 2 goes how many times into 14? It goes 7 times, and it goes 9 times. x3. Okay, this gives us this, but it over also we have that x3 itself is equal to x3. Right. Okay, with this, then we're able to say if you let anything, let n, let x3 be equal to n, then x1 is 2 over 3n, x2 is minus 9n, x3 equals that. That's x1, x2, x3. What is x1? What is x1? Mhm. Let me see what we're getting here. We have these. Wait a bit, need to check something here. Okay, doesn't matter. X1 is the same as 2 over 3, and x2 is minus 7 over 9, and x3 is only n. What is this? Okay, that's what we get. So you can pull out n, 2 over 3 minus 7 over 9. 7 over 9, 1. If you pull out 2/3 out of this, 2/3, goodness me, 1, 2 out of 3. What does this give us? Okay, -7/6. Yes. And then this one, 3/2. So in other words, these two vectors are the same. So somebody can choose either this eigenvector or that one. They just divide by some factor, 2/3. Obviously the n is arbitrary. Okay, we're answering this question, please. Last one, please. For lambda equals 9. Okay, this is just like much. A minus lambda identity matrix times the vector x equals a 0 vector. -6 minus 9. Yeah. Okay. 9 minus 9. So you just subtract 9 from each of the diagonal entries. X1, x2, x3. So you have -15. Here you have -3. So we have this augmented matrix. Okay. And then we can divide through by -15. -1/15 row 1. It's exactly 1, 0, 3 out of 5, 0. 4, 0, 2, 0. So you have 1, 0, 3 out of 5, 0. Row 2 minus 4 row 1, 0, 0. -4 row 1 is going to be -12 out of 5 plus 2, which is -2 out of 5, 0. Row 3 plus 3 row 1. Okay, just row reduction this one. 0, 0. Row 3 is -4 plus 3 row 1, which is plus 9 out of 5. What is this? -11 out of 5, 0. This is very interesting, this. This is very, very interesting. Yeah. So we continue. Right, continuing with this row reduction, it's just basic first year. This matrix theory. Right, so we continue and we get the answer to this. Right, so what we're getting therefore is that we have the following. We continue. Which is minus 5 out of 11, row 3, 0. Minus 2 out of 5 is 0. Row 2 plus 2 over 5, row 3. 0, 0, 1, 0. Row 1 minus 3 over 5, row 3. 0, 0, 0. Okay, this is actually saying x1 is 0, x3 at the bottom is 0, but x2 is x2. And you can let x2 being arbitrary to equal p, for example, so that so x1 is 0, x2 is p, and x3 is 0. You can pull out the p, 0, 1, 0, p is arbitrary. So now p being arbitrary here, okay, we have checked much, but we shall conclude this question here. So p is arbitrary. Now we conclude the question beautifully. Right, so p is arbitrary. Okay. But it's not 0. Okay, eigenvectors are never 0. Right, we continue to analyze this question and to write the conclusion to it. Right. Um, right, we continue.
Hello?
Yes, please.
Why do you minus 9 there?
Okay, that's a good question. The intention was, let me check that. We obviously we're not supposed to use minus a 9 there. Let me see. We're not supposed to minus a 9 there. Um, okay, just 1 minute. Let me check. It's 6. It's 6. Can I just rectify that? See, but I don't expect it to make a huge change. Thanks for realizing that. It must remain 6 in here. Okay, so must remain 6 there. 6 here. So 6 here. All right. Let's see what we're getting. So we divide by the minus 1 over 15. So that's going to be minus 3 goes up in times. It goes 2 times there. It goes 5 times there. So it's a 2 and 5. There's a 2 here and 5, but negative. Right, so we have this. The 2 and 5, so this one here is minus 2 out of 5. Is that right? Yeah, 3 goes 2 times into 6, and it goes 5 times into 15. Right, so we have the 402 is carried forward. So we come here as well. We remove this one. So you have, no. So you have a minus 2 here, like this. Minus 2 here. Okay, let's see now. Um, let's see. Okay. Now you said minus 4 1, so it's going to affect this one here. It's going to affect this. This is going to be affected. And then we can remove these. They're going to be affected. We can just clean this up so that we avoid just errors, and we continue. We clean this up. Right, so we clean this up, we clean this up, we clean this up, we clean this up. Okay, the subtraction obviously must happen only along the main diagonal. So along the main diagonal, so we have just to rectify that. Okay, let me see now. 2. And now here you say row 2 minus 4. Row 1. Row 3 plus 3, row 1. Minus 4, row 1. Okay, so minus 4, row 1 is going to be actually 8 out of 5 plus 2, 10. So 1, 0 minus 2 out of 5, 0. So that's going to be row 2. Yeah. So it's going to be 18 here. 18. It's going to be 18 out of 5. Right, because you're saying row 2 is this one, which has the entry 2, minus 4 of that is 8. And then row 3 plus 3, row 1. What is row 3? It's minus 4. Right. And then plus 3, which is 6 out of 5. What is this? Minus 26 out of 5. So we need to change this one. So it's minus 26 out of 5. Right. So now what we get here? 0, 0, 1. By saying minus 5 out of 26, row 3. We get this. Okay, so you can just write that one out, and then also write this one 0, 0, 18 out of 5. And then now we continue. We continue. Right, so we continue here and we raise this. So what do we get here? Okay, so it's row 2 minus 18 out of 5, row 3, 0, 0, 0. Okay, there's a 0 here, 0. And then here we have row 1 plus 2 out of 5, row 3, 0, 0, 0. So we have these. We have these. Right, so it's the same conclusion because x1 is 0, x2 is x2, and then x3 is that. So we have that x1 is 0, x2 is that, etc. Okay, too many matrices. A bit boring and redundant. So you have x1 is 0, x2 is x2, and x3 is 0. Okay, so obviously here what we did was to say that x2 be p where p is arbitrary. But in this case, p cannot be 0. Why? Because then the eigenvector is going to be 0 because it's only p that is non-zero is a non-zero entry there. All right, so we have this. Right, so we write back now to conclude our discussion, to conclude the solution to this. Right. The dominant eigenvalue here is 9. Because the first question was like, the dominant eigenvalue and the associated eigenvector. So the dominant eigenvalue is 9 because we found the eigenvalues, and the biggest one, the one with the largest magnitude, is 9 because it's 4 and minus 3. Okay, just ignore the signs and check the modulus of each one. And so 9 is the one that is dominant. And for 9, we got the eigenvalue, the eigenvector, excuse. Right, so, well, the dominant eigenvalue, the dominant eigenvalue is 9, and associated, the associated eigenvector the associated eigenvector is 0, 1, 0. Yeah, for 9. So lambda equals 9. The dominant eigenvector, what is it? It's the one that is the largest absolute value, the largest modulus. The dominant eigenvalue is the eigenvalue with the largest absolute value. Okay, so there's this that is the largest absolute value. Okay, so you have this one. The eigenvalue with the smallest absolute value and associated eigenvalue. So we can just give the answer to this one. Right, so we have the eigenvalue with the smallest absolute value. The eigenvalue with the smallest absolute value among the given ones Okay, we're right back. The eigenvalue with the smallest absolute value. Absolute value. Okay. And to say among the given ones. Right, among the given ones, or among lambda 9 minus 4 lambda 3 is lambda equals 3. 3 is the smallest absolute value. With the modulus equals 3. And the associated eigenvector, okay, then we speak about the power method. Eigenvector is, right, so for lambda equals 3, what is the eigenvector? Right, the eigenvector is 1 minus 7 over 6, 3 over 2. Is 1 minus 7 over 6, 3 over 2. 1 minus 7 over 6, 3 over 2. Okay, the eigenvalue with the smallest absolute value and the associated eigenvector. So it's lambda equals 3, and the associated eigenvector is 1 minus 7 over 6 and 3 over 2. But you can take the other one as well for the 3. So you can take either the 1 to 3 over 2, or you can take the 2 over 3 to 1. Okay, they are the same. They just differ by the what? By a factor. Next, we continue. We continue. We continue. Um, what did yeah, okay, I was saying you can choose any of these. You see. Now we've done the B part, we just need to do the C part. Right, the C part is the remaining eigenvalue and associated eigenvector. In all cases, start with the vector 1, 1 and iterate 3 times. Use at least 4 decimal digits. Okay, we are yet to um, just strengthen that. All right. Um, okay, right. So we have exactly that. Right. Okay, I want to say something about part A. I want to say something more about part B, excuse. Right. Okay. I want us to move to look at A in detail, but A in detail, some detail. Okay, obviously the part A, we started by looking at the eigenvalues, all of them in the eigenvectors, but we need to um, further reinforce that by giving the idea of this. So I'm gonna actually give a detailed answer to the idea of the dominant eigenvalue. Right, so we continue. Okay, we continue. All right, there's more we say about the dominant eigenvector and the eigenvector with the smallest. Okay, there's something we call the power method. Okay, which we need to learn for exam purposes. The power method. So the dominant eigenvalues, or the dominant eigenvalue, okay, I'm just going to describe this method first, can actually be found by applying the power method to the matrix A. Thus, for AX is lambda X minus that. What is the matrix A? 492 minus 302. Okay, this is the matrix A. Right. If this is the matrix A, I would want to bring something more to that. Right, so these can be determined as follows. Can be determined as follows. So you equate these to a vector. Right, you equate these to a vector. Right. So obviously, I mean, we have seen that the dominant eigenvalue generally is the one that has the largest absolute value amongst the eigenvalues that are there. Right. So, but if you look at the matrix A, and we take the matrix A as it is given, and I want us to use one result here. Right. I want us to use one result here. Right. So if you use this result here, okay, when you have AX equals lambda X, and you recall that the matrix A is this from the beginning. I'm going to write it on the side here as something I want to do. Right, it's minus the minus 606, like I wrote it. It's 492 from the question, and we have minus 305. Okay, right. If this is the case, then you take this particular matrix, the matrix A, in this equation that says AX equals lambda X. Right. If AX equals lambda X, and for a given value of lambda, right, for a given value of lambda, this matrix A can be equated to 0, 15, then 2. 0, 15, then 2. Okay, I would like first to that we remember the eigenvectors. What are the associated eigenvectors here? For lambda equals minus 4, what is the eigenvector? Okay, so yeah, there's a calculation we're going to do here in view of what we call the power method. Right, so you have that. Let me see. Okay, I want to give a summary of the eigenvectors here and the eigenvalues. So we have lambda equals minus 4. We got the eigenvector to be, we wrote it as a row, and write it as a row still. Right, so what we get here? Okay, this is a powerful method, but it comes in the exam, so we need to be familiar with it. For lambda equals minus 4, what did we get it to be? So we got 3, we got minus 14 out of 3, and we got 1, like that. For lambda equals 3, 1, minus 7 over 6, 3 over 2. For lambda equals 9, we have 0, 1, 0. Okay, we got these vectors there. Okay, I want to give one comment about what we call the power method and how we use it, because it's extremely important that we apply it here, because it is very useful in helping us conclude with a couple of iterations. So I'm going to give a statement of the power method just in a second. Right, I'm going to give a statement of the power method. I'm going to just write it on the screen so that it can actually be known and we can use it. Right, the power method. Right. Okay, just one sec. I'm going to write it on the screen so that we can have it and make sure that we always are able to use it all the time. Right. Because I want us to use it here. I want us to use it there. Right. So we shall get a couple of these. So there is this power method, and this is the statement of the power method. Right. So we have the power method in the following manner. Just one sec. Because I want to give the formal statement of the method. Right. First things first. Yeah. Okay. That is not a symmetric matrix. Right. So like we said, so let me describe the algorithm. Okay, I'm going to describe it. Yeah. The power method. Okay, there's an algorithm we use. Okay, let me just describe the method first. Let me first describe the method first before we use it there. Right. 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 Okay, what is the best way to describe it? Let me describe it with an example. Right, the matrix. Okay, let me use a small example. The matrix A, for example, is the entries -2, -3, 6, 7. Has eigenvalues lambda equals 4, lambda 2 equals 1. So the lambda 1 equals 4, lambda 2 equals 1 minus 1. Okay, no, it's 1. So there are two. I'm just giving a hypothetical example here so that you can use this method, but I want to describe the process first. Right, so we have this one. Okay, if you have lambda 2 equals 1, because this matrix has 1 and 4 as eigenvalues, but the eigenvector here was it's going to be like for you're going to have call this one v1 and call this one v2, which is that if we start with the arbitrary to start with, you start the process of iteration and you use the power method, you start with x naught equals 1 1. Like obviously in that case they suggested we start with 1 1 1. So you multiply by the matrix A, multiply by the matrix A. Okay, so if we do that, it gives us some matrices. Okay, because now we're getting the matrices on the right of that, and I want to explain where these matrices are coming from. So you'd have this one times x0, -3, 6, 7. You have 1, 1. And then this is -5. This is 13. You're going to get x1 that is like this. After you got x1, you started with x0. Then you're going to get another x2. Okay, because you're going to get these things. Then what is x2? x2 is ax1. What is a? Is -2, -3, 6, 7. And then x1, we got it before, is that 13. And then we multiply this, 61. x3. Okay, this will go on. Okay, right. There's a consequence. I'm just describing the power method, please. So we shall go on up to what here? We shall go on as much as possible. So I'm going to say, as a consequence here, we have an observation. So I'm going to state it as a consequence. Um, approximations, because after this, then you can use it in our problem. We're going to use this method to our problem. So Approximations to the dominant. Eigenvalue. Okay, the dominant one being 4 R. Okay. So when I have lambda 1, for instance, for example, lambda 1, for the first step, being exactly 61 out of 13. And then lambda 1, 2, okay. All right. I'm going to write in green. Okay, because now the couple of steps, just that I jumped. So let's look at a couple of these steps. Like, what is x3? Can I write here? We stopped at x2, okay, for convenience, but let's go to x3. So x3 is going to be ax2 minus 125, 253. So I'm saying x3. Then x4 is ax3. ax3 is minus 509, 10, 21. Okay, just multiply the matrices, A with the previous one. And then here you have x5, which is ax4. They're going to stop at 6. And then it's going to be minus 2045. And then you have 4093. And then you have x6, ax5. We have, what is x6? Is going to be exactly minus 8189, and then this one is okay. Just keep multiplying, but yeah, I'm writing the results out because I'm summarizing the whole thing so that you can use this algorithm here. Right, as a consequence, the approximations to the dominant eigenvalue lambda equals 4 is the biggest one. So what are the approximations in view of all of these up to x6? We have lambda 1 to the power 1 in brackets, 61 out of 3 for the first step of the iteration process. The second step is going to be 253 divided by 61. 253 divided by 61. Okay, shall analyze that together just now. And then I'm writing another one, lambda 1, for the most dominant one, the approximations. And therefore, you have this one here is 1021, 253. And then you go on 4, lambda 1, 4, 4093, 1021. 5, 16, 381 divided by 4093. Like that. Okay, look at what we're doing here. First, because now we're dealing with the most dominant one, but we started with 1, 1. Like in the problem we're doing, we're starting with 1, 1. And then the next thing is we took 13, right? We took 13 and we divided by what? We took 13 and divided by, we took 61 and divided by 13. So we took 61 and divided by 13. Right. Or you can say you took 61 divided by 13. So next you took, because this was x2, then x3, you took this one here. You took 253. You took 253 divide. So you take the next one and divide by the preceding one. So 253 to divide by 61. Then we took 1021, we divide by 253. 4093, we divide by 1021. 16381, we divide by 4093. Okay, upon this divisions, then you get the calculator, the decimal equivalence of these. Right, so we have that. Okay, I'll just mention more details obviously here. Moreover, so we're saying as a consequence, the approximation to the dominant eigenvalue, these are the approximations. But this one here, okay, let's look at the approximation so that this thing can make sense. This is 400. So we stop here because this one is closest to that. So this is 3, is 2. 400, 200. Use a calculator. And then the 1 to the 4th power is 4, 0081. Right. So obviously this process can continue as much as possible. Right. What is the 61 out of 13? It is exactly 4.69. We shall use this method to do our problem. 2, 3, and then this one, 253 over that is 4.14754. This one, 1021 over that, over 253, 0, okay, 3, yeah, 0.3557, like this. All right, so an approximate eigenvector corresponding to, okay, I want to give this comment. So there's something called an approximate. Okay, yeah, I'm just describing the algorithm with a small example. Right, so an approximate eigenvector corresponding to lambda 1 to the power 5, which equals 16, 381, which is 4093. So the approximate eigenvector corresponding to this one. Okay, just one sec. 00200. The approximate eigenvector corresponding to this one is x6. Okay, because that would be at 5. So the corresponding eigenvector is x6, just one more. Right, and x6 is what? We got x6 already. Is this one here at the bottom? Bottom right. So it's minus 8189,16381. which divided by minus 8189 normalizes. Okay. Normalizes to 1. Okay, we're getting to this. 0, 0, 0. 3, 7, which is approximately vector 1. This one here. Okay, just you pull the obvious what I'm describing an algorithm here. So this is 1. Right. So you can see therefore that at 6, you can always go through particular steps, but you can see that at 6 we have the estimate that is V1. Right. So in other words, what are we saying here? We have found the approximate vector corresponding to the 5th one. And it is x6, which divided by minus 8189, this is the upper entry here, normalizes to this. All right, so if it's normalized to that, it gives us exactly the first vector that is associated with lambda equals 4, which is the dominant eigenvalue. Okay, right, so we actually therefore do this in our case. I want to mention that. So here, for example, we do the same. But obviously our metrics are a little bit larger, but need to understand the algorithm called the power method. Right, and then you're gonna perform further divisions. Okay, I just wrote that, but maybe let me start with the 1, 1 vector. Okay, to make the thing a bit clearer. Right, if you start with the 1, 1 vector, you multiply. So what is this? You start here, this is the matrix A, you multiply with 1, 1. So we are dealing with A x naught, and ax naught is going to give us vector x1. Okay, this is what we get. And these vectors now, we can normalize these here. We normalize this. Okay, let's get the result here. Okay, so if you multiply these by the 1, 1, what do we get? Okay, here you multiply these here, it's going to become 0. Row by column, row by column. It's going to be 4 plus 9, 13, plus 2, 15. And this one is going to be minus 3, 0, 2, minus 1. Okay, so we get this here. So that gives us x1. What would x2 be, for example? Right, so if you have these, what would x2 be, for example? So now I'll take okay. Moreover, I want us to analyze these in view of the fact that the dominant eigenvector is 9. The dominant one, dominant eigenvalue, excuse me, is lambda equals 9. Okay, if it is lambda equals 9, what is the vector? We saw that it was 1, 0, 1, 0. Okay. And therefore, if it's 0, 1, 0, we can factor out the middle entry, 15. And if we do that, 0 here. Okay, there's a mistake here. This is 5, excuse me. Okay, this is 5. In the matrix A, it is 5 here. It's going to change this one. Right, so in other words, this one is 5. And therefore, if you multiply these by that, it's going to be minus 3 plus 5, 2. So if you pull out 15, it's 1, and then 2 out of 5, 2 out of 15. Right, and 2 out of 15 is 0 0.1, 3 sort of recurring, like that. Okay. The next step in the process, we take that vector, we take the matrix A, 0, 6, 4, 9, 2 minus 3, 0, 5. You multiply by the previous one, the 0, 1. Okay, here you can put 2 out of 15, or you can put 0 0.1 and the 3 threes, like this. Okay, if you multiply these, what does it become this? Right, multiply these, you can use a calculator to add this up, but it becomes 0 0.8, 3 zeros. And then you have 9.2. Okay, you can multiply this out. This is row by column, row by column. We just have some decimals, obviously, in this case that are cropping up. So we have 9.2667, 667. And then you have 0 0.6667. Okay, so you get this one. Now, in view of the fact that this one is the 0, 1, 0, so we desire a 1 here. So if you desire 1 in the middle, we're going to pull out the 9.2667. Okay, so you divide like every entry by the 9.2667 because it's 0, 1, 0, the associated eigenvector. So it's going to be 0 0.0863. 1 here, 0 0.0719. Okay, so these are like 2 iterations. So after 2 iterations, we obtain what do we obtain? We obtain a couple of values of lambda, but we got lambda equals 9.2667. We got an eigenvector, which is 0 0.0863. 1, that is the eigenvector, is this one here, 0 0.0719. After those 2 iterations. Okay, so we're gonna be shorter and brief. After 10 of them, you can do 10. after 10 of the iterations, right? Can continue like we did. We factor out, you just multiply the matrix A with the preceding vector. Right, so after 10 iterations, normally the exam is not so long. After 10 iterations, we obtain okay. After 10 iterations, we obtain lambda, like just got now. Obtain lambda equals 8.9939 and a 4. 0 0.0011 zeros here, 4 of them. Okay, we continue like this. But after 10 iterations, because after 2, we got the 9.266. Then you can go on after 10 iterations, then we shall get the lambda equals 8.994, 3 nines. So what do we do with all these here? So compare this. Compare this with the result in Roman figure 1 when, okay, the result in Roman figure 1 when we look at dominant eigenvalue being 9 and p equals 1. Okay, because we got the eigenvector to be 0, 0, 1, 0. We got 0, 1, 0. When lambda equals 9 and p equals 1, and that is a 0, 1, 0. Okay, because we got 0, 1, 0. And that means p is 1. Sort of. Okay, to get that eigenvector. After more iterations, so we compare with the results when lambda equals 9. So the more iterations we take, the more accurate the result gets. What result are we talking about? Obviously, it's the more this value here, which sits here, which is the eigenvalue. So we get the approximations of this eigenvalue. Okay, so getting the approximations of this eigenvalue, the number that sits here becomes the eigenvalue we want. And now we know very well that the dominant one is 9, and then the approximate ones now, after 10 iterations, we get these. Okay, so we're just showing that after more iterations, we get closer and closer, and we get a more accurate value of lambda than when we started. So we've used the power method here to solve this problem. So the question was, okay, here was the question. Consider the eigenvalue problem this, okay, let me come here. Right, you consider the eigenvalue problem with the matrix A and its inverse. The dominant eigenvalue and the associated eigenvector. Okay, we've already found the dominant eigenvalue to be 9, and the associated eigenvector to be the 0, 1, 0 vector. In all cases, all of them, start with the vector 1, 1, 1, and iterate 3 times. Use at least 4 decimal digits with rounding. Okay, so we have done the first one. I think that I will have to do, I will have to finish this question. Let's just push it if we can to finish this question, just to make sense of this method in view of the dominant, the smallest eigenvalue, and the remaining one. Okay, would have done justice enough to this method. Okay, it's a bit lengthy. But now I want us to look at the next question, which says the eigenvalue with the smallest absolute value and associated eigenvector. So we continue with these iterations. Right, let's just do that one. Right, for the C part, the B part, excuse me. The smallest, I'm going to write the smallest. I want us to make sense of the power method here in the eigenvalues. Right, the smallest absolute value or rather the smallest eigenvalue right. So the smallest eigenvalue okay, let me describe here, can be obtained by computing the inverse of A. And then using the power method. The power method, because okay, we always start with AX equals lambda X, because that is the eigenvalue eigenvector equation. At this point, we can multiply both left and right by the inverse of A. So multiplied by the inverse of A. So there's X here. So we're getting X equals A inverse lambda X okay. And so you can divide by the lambda, not 0, and have X over lambda. Right, and have X over lambda is equal to A inverse X. You can get this equation. Okay, the smallest eigenvalue can be obtained by computing the inverse of A and then using the power method because of that. Okay, so in other words, I want us to look at the converse of this. Right, and conversely, we start with A inverse of a vector X equals mu X. Okay, this is the eigenvalue eigenvector equation, just that we've written it like from the end, A inverse vector, etc. And then the 1 over lambda coefficient of x can be written as mu, Greek letter. A inverse x. We can solve for x by multiplying both left and right by the matrix A, and we get that. Right. But what is A inverse? You can equate this one. Okay, you can equate now the A inverse x is the same as mu x. So this is A mu x because A inverse x is mu x. So you can write like that. A mu x. So AX. Okay. Okay, let's use this result. And let's use this result. I want us to use it very, very carefully to our problem. So in other words, now we can just use the inverse. What is the inverse of A? Right. So we remember that the matrix A is minus 6, 0, 6, 4, 9, 2, minus 3, 0, 5. And A inverse, thirteen out of 54, 0, 1 over 9, 0. 1 over 2 minus 1 over 3, 1 half. Okay, this is the inverse. How do we use the inverse now? For the smallest one, it becomes convenient to use this method. Use the converse of the former. Well, it uses the inverse. This method uses the inverse. So you can use the inverse for the smallest one, for the smallest smallest absolute value. Okay, let's just demonstrate this method here. Okay, so what do we do here? So we're gonna then have minus 15 out of 12, 13 out of 54, 1 out of 4, 0, 1 out of 9, 0, 1 out of 2 minus 1 out of 3, 1 out of 2. Okay, we start with this. They told us to start with the 1, 1, 1 vector. Right, if you multiply everything using a calculator, You'll get 0.0833. You'll get 0.0185. 4 decimal places. 0.2500. Now we got this one. But you compare this with the original thing. Rather compare it with the equation, this one. Compare it with that one. Or if you compare it with that one, what is the smallest one is lambda equals 3. The smallest one is lambda equals what? Is lambda equals 3. But what is the eigenvector? Say it with that. We wrote it, but I'm going to write it down now. We wrote 1, then we wrote -7/6, and then we wrote 3/2. Okay, so lambda equals 3, we got that one. Now we are using it here. We are using it here. Okay, gonna do it now properly. But like I said, you can have this one, or you can have the two of them I wrote. What is the other one? The two of them. Well, lambda equals 3. Right. So this one also that is ends with a 1. So the one that ends with a 1, just note it. Right. So let's use it. Either use this one or that one. So if you use the one that ends with a 1, right. So we said you use that one or you use this one here. Okay, we're taking from the other side. The one that ends with a 1, but the equivalent. So it's 2/3 -7/9 and 1. Okay, so you have the smallest one, and which is 3, lambda equals 3, and then the eigenvectors associated with it. Right, because the one that ends with a 1 makes us therefore desire. It makes us to desire to have, so you can use either face to that. This one. So we want to make this one 1. How do you make this one 1? Divide by it. So we're going to divide by 0. That one, 0.25. And if we do, what do we get if we do? Okay, divide by 0.25. And then you factor out 0. Okay, equals 0.25. So if you factor out 0.25, what do you get? You get a 1 here, because you want to resemble this one. And then what do we get here? We divide this one by 0.25. Which is 0.0741. Divide this one by 0.25. 0.43. 1, 2, 3, 4. Okay, want it to resemble that, so we consider the other version that ends with the 1, so we have that. We continue. We have this one. Minus 15 out of 12. 0, 1 out of 2. Okay. Ups. I need to move to the next slide. So you'd have, okay, what is the inverse of A? This is minus 5 out of 12. That's given the question. 13 out of 54. Minus 1/4. 0. 1 out of 9, 0. 1/2. Minus 1 over 3. 1 over 2. Now you take the previous one, which is the 0 with the 3's and the 0, 0, 7, 4, 1, and then the 1. Multiply the inverse of A by that one. 4 is 0.3333. 0.0741, 1. Okay, multiply. This is more interesting. Okay, row by column multiplication. This row by this by that, this by that. But if you multiply and use a calculator to just convert your decimals, it becomes 0.3611 minus 0.2449, and it becomes 0.4167, like this. All right. And then now we used that other one that has a 1 at the end, so you must factor out this one. So if you factor out 0.4167, you sort of like dividing by the 0.41. So this is 1, and then this one is going to be minus 0.5877, and then this one is 0.8667, like this. Right, after 2 iterations, we estimate the dominant. After, okay, we've done just 2 iterations. Okay, let me maintain this one. Right, so after 2 iterations, we have the following. Right, so we continue. After 2 iterations, we estimate the dominant eigenvalue. So it becomes the dominant eigenvalue of the inverse. Eigenvalue of A inverse S. Right, so it's the one that sits here. 0.4167, because it's always AX equals lambda X, but you can stay, we stated that in terms of the inverse, or in terms of the inverse, we said it actually means that A inverse X is 1 over lambda X. Okay. Okay, what we get? Right, and the corresponding eigenvector and the corresponding eigenvector. Okay, this is 4167. The corresponding eigenvector is 8667, 0.58 here, 77. Okay, we're just copying this one and then 1. This is the eigenvalue, and that is the corresponding eigenvector. Right. From this now, this in equation we just got associated with the inverse. We use the inverse of A to get this. The eigenvalue of least magnitude of A is therefore right. So is therefore lambda of least magnitude we divide by 0.4167. Okay, we use the word dominant, but obviously we're looking for the one of the smallest absolute value. But use the word dominant because it was the inverse. And then now divide 1 by that, 4167. What is the result? 2.4. 3. 0. It doesn't matter the number of zeros. And the corresponding eigenvector is in the corresponding eigenvector in the corresponding eigenvector is given by the eigenvector above. Okay, so the corresponding eigenvector is the green one there. Okay. Now we note after 10 iterations. Okay, Mary, can use a calculator to do this. After 10 iterations, because it's going to be long, but yeah, state. After 10 iterations, we obtain after 10 iterations, we obtain lambda equals 1 divided by okay, so you'll see there's something when I get a number like here, but it's 3407 after 10 iterations. And this, if you divide, is 3.935. Okay, you can see that here, this one was 2.4, which is very far from 3. But this one now, after 10 iterations, is getting closer and closer to 3 because it was 2.4, but now after 10 iterations, it's like 2.935. So we can see, therefore, it's closer and closer to 3. But most importantly, the eigenvector associated with it, which is we're going to get when we factor out, when we get this number, is going to sit like the green one, right? So it's 0.6884. 7805 1. Compare this with the result. Compare this. Okay, this with the result. In the first Roman figure, when lambda was actually 3, and the n was 2 to 3. Okay, it's the n inside the vector. So we use some m, n, and p. So you'd get therefore that x would be 2 over 3 minus 7 over 9, 1. Okay, you remember the vector was like this. And therefore, if the vector was like this, then you can write is 0 0.1, 2, 3, that 0 0.778. Um, right, so it's 778. Okay. Now we compare this with the result when lambda equals 3 and the n equals that, so we have that. So obviously we remember that when lambda was 3, we got this eigenvector. But now after 10 iterations, we got this lambda equals 2.935, which is close to 3, and the eigenvector is this one. The convergence of the power method is slower than in A because of the magnitude of the dominant eigenvalue of the lambda is 1 over 3. Okay, I'll mention that. All right, long calculation here. The convergence, I'll just give a comment. You see that it was lower than in the first dominant case than in part A. So the convergence of the power series I want to say the convergence of the power method and just the power series. The convergence of the power method. The convergence of the power method is slower than in A. Okay, in A it was faster. This is because the magnitude of the dominant eigenvalue of A inverse. 1 over 3 is both. Is not much larger than that of the eigenvalue of the eigenvalue with the second largest magnitude. Okay, we shall analyze this here. Second largest magnitude minus 1/4. Okay, the convergence obviously of the power method, we say, is slower than in A. In A, it was faster because the magnitude of the dominant eigenvalue of A inverse, 1/3. Okay, because now if it's A inverse, the eigenvalue is 1/3. It becomes 1 over, because it was 3. It's not much larger than that of the eigenvalue with the second largest magnitude, which is minus 1/4. So now what you're seeing here is that you have comparisons, but also you actually are seeing that the convergence is actually much slower. But we have certainly found the eigenvalue. Okay, so in other words, the estimated, hey, we might take a break now. We'll take a break. Okay, so obviously we can see that for lambda equals 3, which is the smallest one, the estimated eigenvalue is 2.935, and the associated eigenvector is that one. Okay, I think we need to take a break. The time is exactly 15. The time is exactly 15:45. We started at 13 hours. Yeah, let's take a break. We'll continue tomorrow at 1 p.m. Okay, I'll try to bring more interesting examinable questions, but also I'll look at better ways and simplified ways of doing the problems, perhaps more comprehensive. Right, so what do you do today? Just try to make sense of the things we've learned and look at the problems we've learned. What problems did you learn today? Basically, we solved 2 questions in detail, just left with one to conclude the whole problem. So just try to make sense of these things and make sure that in particular we dealt with the smallest absolute value and we estimated the dominant eigenvalue, we estimated, we found the estimate using the power method in each case. And obviously, I'm sure there is some good time to take a break. You can actually just try to make sense of the things we did. I'll try to bring more comprehensive exam type questions that will take us towards covering the exam methods that must be learned. So what method did you learn today? We learned the power method, right? Need to be, I will actually try to bring much nicer and shorter example as well to highlight these in the best of ways. But I think that I must thank you for today. I'll see you tomorrow at 1 p.m. Okay, we don't have much time left before the exams. It's crunch time. So I wish it's my plan that we meet tomorrow and push as much as we can so that we can make the most of this module here. Okay, right. So thanks a lot. I'll see you tomorrow, 1 p.m. All right. Thanks. Goodbye.